And I kind of kept it junk because students get the idea that everything, if a factory doesn't build it, it doesn't work. And so I tried to impress them that, doggone it, somebody had to build that stuff at the factory. So it's junk, and I might add that tonight is the first night I'm using solid state. I retired my old Motorola 1948 transmitter tube, and so if I blow up this solid state job, the demonstration stops. So at any rate, antennas and transmission lines have to go together, and so I'm going to look at SWR and so forth. I have a reflectometer here, which most of you are familiar with, the Bird Model 43 reflectometer. This is the guts out of the 43, and I'm one of the bigger meters, but I only had a 50 microamp, and Bird uses 30, so I had to recalibrate a meter. So this is, again, the standard reflectometer for forward and reverse power. So you're all familiar with Z-sabos and impedances and so on. And incidentally, here's where the demonstration is going to end up. Do you still have any in Michigan Electric Power here?
Yeah. It's AEP.
AEP, American Electric Power.
Correct.
We have NIPSCO, and you have gas, I guess. So anyway, NIPSCO went on strike many years ago, and a ham friend of mine was in the microwave division of NIPSCO, and he was considered administrative, or what is it you call it, non-union. And so he was going to be locked in the generating station up on the lake. And so NIPSCO bought all these parts for him to play around with. And just a simple circuit, and close the switch and the lights light. Open the switch, the lights don't light. And close the other switch and the lights still light. And so on. Okay.
That's great.
So NIPSCO paid for all those parts. Okay, so let's take a transmission line that has, in this case, 50 ohms. And incidentally, where did that 50 ohms come from? Anybody know? In 1941, the U.S. Navy had a conference in Washington to try to figure out how to use shielded coax cable instead of using open wire line running across the bulkheads and everything else. And so they got together and with industry, and they looked at the various cables. 33 ohm coaxial cable, which of course that's a difference of ratio of the inner to outer conductor. 33 ohms will give you allow you to use the highest voltage. 77 ohms will be the highest efficiency. So they figured, well, where are we going to get, which do we want, 33 or 77 or somewhere in between? And somebody comes up and says, where are we going to get this coax cable? Well, we're going to make it out of copper tubing. Who has copper tubing? The plumbing industry. What dimensions does the plumbing industry have that we can put one inside of the other? And it turned out that the dimensions that worked good to give some kind of a reasonable voltage breakdown versus loss, turned out that the dimensions that they had, the copper tubing that they had, dimensions, turned out to be about 50 ohms. And that's what they adapted that to. Then in many years later, here's RG8 at 52 ohms, and you got Heliax at 51.5 and 53.5 and so on. And many years ago, the IEEE, Institute of Electronic and Electrical Engineers, adopted the policy that if it's close to 50 ohms, we call it 50 ohms and we work with it at 50 ohms. So if it's 2 ohms off, what makes a difference? So okay, here's some cable, and if I send some power down there, there's the power going down here using an open circuit. There's the power coming back. Everything going down is coming back. So we're not gaining any. If we put a short circuit on here, we probably load the transmitter a little different, but we still should have all the power. There's the power going down, and there's the power coming back. Everything's coming back, so we're still not obtaining any work out of it. So 50 ohm cable, let's terminate it in 50 ohms. Actually, I'm using 47 ohms, so it'll be a slight mismatch. But if we terminate in 50 ohms, we should absorb all the power going down and nothing coming back. So let's see what we have.
Oops.
So we're absorbing all the power. That didn't work out very good. That was supposed to explode. I pulled this in class one time years ago.
Flame-proof resistor.
Kids set up, we had a regular school test, and he was setting up on the back seat so he could see this curve back and back. And I turned that thing on, and that thing, bang! He jumped up in the air off of that chair. So, most of you guys are familiar with Heathkit. Heath got the idea many years ago of putting a 50 ohm resistor in a paint can and filling it full of oil. And this is one of their lab original cantennas that they gave it to me one time. So if I put that cantenna on there, I should absorb most of the power. Wowie. There's the power going down, and there's the power coming back. Perfect load. Perfect termination, I should say. Well, perfect load. A little more sensible and dummy antenna. Here's one that if you're not running much power, here's one from Radio Shaft.
Radio shaft.
Oh
yeah,
That's fine.
Sneaky, I didn't know you'd squeal on me. So there's the power going down, there's the power coming back, so it terminated pretty well. Many years ago, we got a whole truckload or truckload of equipment from Page Television when they were in Michigan City. They were changing models on something that 1200 ohm resistors had a whole great big box of them, so I grabbed a calculator or slide rule at that time and figured, so let's see, I got 24 1200 ohm resistors would be pretty close to 50 ohms. And so at evening I cut out 2 pieces of copper, and I was giving final exams the next day. So I'm just sitting up in front of the classroom watching all the cheaters. And so I built this one, soldered it while they were taking exams. And it turns out it's about 53 or so ohms, which is close enough for government work. But with these 2 copper plates, I got an awful lot of capacity. On 40 and 80 meters, this thing works beautiful for 48 watts dissipation, but at 2 meters, the capacity there is atrocious. So I got a little stub on here, a transmission line stub shorted, less than a quarter wave is an L, so that L across the C resonates it, and so the capacity disappears. So I should have a pretty good. There's the power going down, and half a watt coming back, so looks good enough to get something fixed. Okay, if we piece of wire, that's got the tops mixed up here. If we cut a piece of wire a half wave long, it becomes self-resonant, and we have a standing wave of voltage on that wire like so. And current, there can't be any current at the ends, so current on the wire will look like so. So let's check that out before we go any further. And let's terminate in an antenna that's cut reasonably close to a half wave. I'm having trouble with coax connectors tonight.
You still call me sneaky, after all these years.
I didn't do that. Wheaton's the one that
Yep.
came up with that
Yep.
name.
Uh-huh.
What?
Yeah, it caught on pretty good.
This thing should be reasonably close to a half wave. Let's check it. Yeah, there's the forward power and got about a watt or so coming back. So it's not a perfect match, but I should have a high voltage at the end. Go down to a minimum voltage, not zero. This drawing, when we draw this, boy, I missed the middle of it.
Pretty close.
When we draw the standing wave like that, it looks like the voltage at the center goes to zero, and it actually doesn't. But there's the voltage, high voltage at the ends. Both ends have high voltage. Comes down to a low voltage and back up.